Finally reach a new topic. So the next new topic is discrete random variables. It's a probability topic, and we're going to look at probability distributions. So for the first case, we're going to say that discrete random variables describe possible events that may occur for an experiment. So if we have the discrete random variable x, and we're saying that x equals 3 for a coin toss, and we're going to specifically toss a coin 3 times, Px equals 3 could describe 3 heads. It could equally describe 3 tails, but in this case I'm defining x equals 3 to be 3 heads. If I had Px is less than 3, I would have that representing the case where only 2 heads are tossed, or 1 head is tossed, or no heads are tossed. But specifically not the case where we have 3 heads, because x is less than 3. Now to calculate the probability that we get 3 heads, e.g. Px equals 3, we'd work out the probability of 3 heads occurring. So underneath here I've listed the sample space for tossing a coin. If I toss 3 coins, I could get 3 heads, I could get 2 heads and a tail, I could get a head, a tail and a head and 2 tails, a tail and 2 heads, a tail, then a head, then a tail, or 2 tails, then a head, or 3 tails. Now if I look at this whole sample space, there's only one possible case where out of all 8 of them, and not all 8 are equally likely, one chance out of 8 of getting heads, heads, heads. So therefore the probability of getting 3 heads in this notation is 1 over 8. Now x is less than 3 is every case where we don't get all heads. So I've said over here probability of not getting all heads, which is the same as saying probability where the number of heads we get is less than 3. So we're getting less than 3 heads each on our coin tosses. And if we look at all these cases, all of these ones over here have less than 3 heads being made. So that's 7 out of 8 of them. Now, we could have said lowercase p, 1, 2, 3 in this case, and P0 would have been no heads, P1 would have been 1 head, P2 would have been 2 heads, P3 would have been 3 heads. But we lose the ability to do these sorts of statements if we're just using lowercase p. But P of x is the probability of an event occurring. So P of 3 would have been 3 heads. Right, let's keep going. So here I've drawn them out in a distribution table. So this describes all the possible cases for P1, P0, P2, and P3. So for P0, we would have only had TTT, which is 1 out of our 8 choices. Now, for P1, we could have had 1 head first and then 2 tails, 1 head, a tail, a head, and then a tail, or a tail, and a head. So there's 3 cases out of the 8. Here it is here. Now, if we're looking at P of x is less than or equal to 1, or the cumulative total thus far, so the 1 case and all the cases below it, so including the 0 case, that would have been 3 out of 8 plus our 1 out of 8, which gives us our 4 out of 8. Or we could have had, for our 2 head cases, here they are here, that is 3 different ways that can occur. And if we count the 2 case, the 1 case, and the 0 case, e.g. Px is less than or equal to 2, that covers 7 out of our 8 events. 7 out of 8 events here. Gives us a probability of 7 out of 8. And if we're looking at our heads, heads, heads case, there's only 1 of those. And if we add up the heads, heads, heads case in every preceding case, we get 1. And we know now that we've captured all the possible cases. And in doing so, we have completed our probability distribution function. In our probability distribution function, for all values of x, for all cases that we're looking at, the individual probabilities must be greater than 0, and also less than 1, I might add. less than or equal to 1, and the sum of the probabilities have to equal 1. So if I add all these probabilities up, I'm going to get 1, and all the probabilities have to be greater than 0. And that covers, this statement here covers all cases that construct a probability distribution function. I should go back for a second. If we can ever establish that this is not true, either this or this, it's not a probability distribution function. So let's have a look at the first case that we're given in the examples. Just by eyeballing the distribution, we can tell that this is not a probability distribution function because px equals negative 0.1 here. Now you can see that this still adds up to 1. So that satisfies the second criteria, which is this one here. But it doesn't satisfy this first criteria because one of the probabilities is less than 0, and we know that that's a nonsense. Probabilities have to lie between 0 and 1. So p of x is not a probability distribution function as p0 is less than 0. That one is a problem. In B, these do add up to 1. They are all greater than 0. Therefore, we do have a probability distribution function. Tick. In 11.2, we're given a different sample and we need to look at it. So we've been told that px equals x over 10 for these 4 values. And if we add up 1 over 10 and 2 over 10 and 3 over 10 and 4 over 10, funnily enough, we get 1. So this is a probability distribution function. There's no probabilities created by that and these values that give us a negative. And we can do some calculations. So the probability of getting, the probability of getting 2 or 3 in however this is generated would be 2 over 10 plus 3 over 10, which gives us 5 over 10 or a half. This one's a bit more difficult because they've given us this given symbol and we have to rely on our probability rules. So in this case, we want to know the probability of getting greater than 2, greater than or equal to 2, so 2, 3, and 4, but only where x is less than or equal to 3, so we would have to exclude the fourth case, because that's equal to 4, and outside of our bounds. So to do that, we would use our probability function, which is this thing has a name, a conditional rule for probability. We'd find this probability where it has the intersection with this and then divide it by that. So in this case we found the probability of that being a half, which is x is greater than or equal to 2, which is these two here. So 2 over 3 plus 2 over 5, 2 over 10 plus 3 over 10 is 5 over 10, which is a half. And we ignore this case because we know that it doesn't intersect with that bound. And then divide by this probability, so the probability of these three, so 1 over 10 plus 2 over 10 plus 3 over 10, which is 6 over 10. And we find out that the probability of this is 5 over 6. This has absolutely no context, so it's a little bit harder to understand. You just follow your probability rules and the answers come out. Here's a case that does have some context. We've got a box with 3 white and 2 red balls in it. 3 balls are selected without replacement, so we take the balls out and we don't put them back in. Now we can do this 2 ways. We can either draw a tree diagram, which is a little bit more complicated, but is easier to understand, or we can use our combinations from last year, which is simple as a calculate, but is a little bit more difficult to understand. So let's do this first, because computationally this is easier. We're going to choose, look at our 3 cases. In the first case, we're going to say, all right, we get all white out. What's the probability of that? So we get no reds. Out of the 2 red balls, we choose none. Out of the 3 white balls, we choose all of them. And out of the 5 possible balls we could have chosen, we chose 3. So this gives us the probability that they're all white, and that's 1 over 10. And you'd stick that in your calculator. For the second case, we want 1 red. So out of our 2 red balls, we pick 1. Out of our 3 white balls, we choose 2. Out of our 5 balls, we choose 3 of them. And that gives us a probability of 6 out of 10. If we chose both red balls, we would have to choose 1 white ball out of our 3 balls chosen. And that gives us a probability of 3 out of 10. If we add these 3 probabilities up, we get a probability of 1. They're all greater than 0, therefore this is a distribution. And then we can use it to solve some problems. The probability that x is less than or equal to 0 is just that case. The probability that x is less than or equal to 1 is that case and that case, which gives us 7 out of 10. And the probability that x is less than or equal to 2 is all cases, which should give us a probability of 1. Problem solved. Now, if we're doing it with a tree diagram, it's a little bit different. We have to walk our tree. So we get the first ball out of the bag. That's these 2 cases here. The probability of getting a red ball is 2 out of the 5 balls in the bag. The probability of getting a white ball is 3 out of the 5 balls in the bag. So if we got a red ball the first time, we've taken 1 ball out of the bag now, so we've only got 4 left. Of those 4, 1 of them is red and 3 of them is white, because we took 1 red out the first time. So these are the 2 possibilities that can occur. Now, if we've taken both red balls out of the bag, we have no red balls left, so there's no chance of us picking a red ball. We must have chosen a white ball, and that's where this 0 and 1 comes from. And in fact, this can't occur, and that's indicated by the 0 over here. Now, if we took a red ball out first, and then we took a white ball out, we would have 3 balls remaining. 1 of them would be red, and 2 of them would be white. If we took a white ball out and then a red ball, we would have 1 out of our red balls left and 2 out of our white balls left. And if we took 2 white balls out, we would still have 2 red balls out of the 3 remaining balls, and we'd have 1 white ball out of the 3 remaining balls. Now, if we multiply the probabilities of each part of the tree, we get these. And if we're looking at the probability of getting 3 white balls, it would be that times that times that, which gives us 1 over 10. If we're looking at the probability of getting 1 red ball, we would look at all the 1 red ball solutions, which is this one, and this one. As you can see, red, white, white, only 1 red ball. Multiply those probabilities together, add them up, and we would get 6 out of 10. If we're looking at the 2 red ball probabilities, so like this one here, this one here, this one here, and multiplied out the probabilities and added them up, we would get 3 out of 10, and that would give us 10 out of 10 the same way. This logically is a little bit easier to see. This is miles easier to calculate. And that should be enough to do exercise 11.1. Sorry that was a bit long, but there was a fair bit there. It's a new topic. Ta.